My name is Sheng, and I am happy to present the following joint work with my advisor, Matt Kay. The title of our paper is To Cut or Not to Cut, a Systematic Exploration of Y-axis Truncation. So to start, here's an example of a truncated bar chart from Fox News. Most would argue that truncation in this case produces a misleading figure exaggerating the difference between now and January 1st, 2013. Here's another example in which the global mean temperature between 1850 and 2006 is plotted into a line chart that starts its y-axis from 0. This is a case where truncating the y-axis is perhaps needed to demonstrate the severity of temperature increases across the years. From these two examples, we see that there have been different views on whether, when, and how we should truncate the y-axis. In our work, we study y-axis truncation from a different angle. We propose a theoretical framework to understand y-axis truncation, and we conducted an experiment to test hypotheses under our framework. Our results corroborate existing findings, and we also provide a summary of the existing recommendations on axis truncation using our framework. Now, to introduce the problem at hand, let's consider a very simple example. Suppose we want to map the following dataset, A60, B90, to a bar chart. Now on the left, we see the corresponding bar chart. Now suppose we want to truncate the y-axis so that it starts at 50. This produces a truncated bar chart as we see on the right. Note that the difference between A and B, which was originally mapped to a visual difference of 30 divided by 100 times L, is now 30 divided by 100 minus 50 times L in the truncated graph. In short, truncation exaggerates the visual difference between A and B. However, the relation in data space remains unchanged after truncation in visual space. The fact that 90 is greater than 60 remains true if we compare the length of bar B to the length of bar A. Naturally, this prompts a question. Are there other relations that remain unchanged after we truncate? The short answer is yes, but for that we need to consider a more complex example. Now, given the following dataset A155, A285, B150, and B270, we have the following graph on the right, and the following data relation, delta A bigger than delta B, and delta A divided by A1 bigger than delta B divided by B1. Now we can use this graph to answer different questions, such as what is the minimum value in group A, what is the maximum value in group B, etc. Now to go back to the question we posed earlier, under what truncations do the underlying data relations still hold in visual space? Note here that the above two inequalities implies the following two inequalities. Observe that the first inequality always holds, regardless of how much we truncate, because the denominator is the same. For the second inequality, we can do a little thought experiment and treat this as two different truncations. What I mean by this is that we can think of this grouped bar chart as two separate bar charts, and each group has its own truncation. This allows us to write the original inequality, delta A divided by A1 minus T bigger than delta B divided by B1 minus T, into delta A divided by A1 minus TA is bigger than delta B divided by B1 minus TB, which then allows us to plot the relationship between TA and TB. So here's the TA and TB axes, and the maximum value that these truncations can take is bounded by A1 and B1. Here, the 45-degree line corresponds to truncation where TA is equal to TB. The shaded region corresponds to all possible truncations that retain the underlying data relation. That is to say, data relations delta A bigger than delta B and delta A divided by A1 bigger than delta B divided by B1 still holds in the visual space. And also the non-shaded region here corresponds to all possible truncations that reverse the underlying data relation. In our paper and in most scenarios, group A and group B are always in the same frame, so truncations will only happen on the 45-degree line. When truncations are on the 45-degree line and in the shaded region, these truncations correspond to monotonic truncations, or in other words, truncations that retain the underlying data relation. And when truncations are on the 45-degree line and in the non-shaded region, these correspond to the non-monotonic truncations. In other words, truncations that reverse the data relation. Now, for example, here's an example of a monotonic truncation where we start the y-axis at 20. In the truncated graph, it does seem that delta A is bigger than delta B, and delta A divided by A1 is bigger than delta B divided by B1. Now here is an example of a non-monotonic truncation when we start the y-axis at 45. In the truncated graph, it seems that delta A is bigger than delta B, but the relationship between delta A divided by A1 and delta B divided by B1 seems to be reversed. Inspired by prior research, we proposed the following model. Data corresponds to visual forms correspond to task. What I mean by this is that given the particular dataset D, in the space of all possible datasets, big D, D could be mapped to a set of different visual configurations, VD subset of V, some more structure preserving than others. Now for each feasible visual configuration, it can be used to answer tasks, be it low level or high level. While some visual configurations provide more affordance for certain tasks, others may support better perceptual accuracy. What this model allows us to do is that it allows us to examine the nature of these correspondences between data, visual forms, and tasks under the specific example of y-axis truncation. Specifically, if we alter the visual configurations in a way that preserves the inherent structures in data, how does it affect user performance on different tasks? And formally, if function f is a structure-preserving function applied to visual configurations, would d of fv of t be much different than d of v of t? And what can we say about the properties of such a structure-preserving function? Connecting our proposed model to y-axis truncation, a monotonic truncation on the y-axis is simply a structure-preserving function. We hypothesize first that monotonic y-axis truncations will not affect user performance much. That is, d of vt should behave similarly to d of fv of t. And we also hypothesize that non-monotonic truncations would have a more adverse impact on user performance. We designed a mixed factorial human subjects experiment. The between subjects component is that each participant is randomly assigned one of 4 possible tasks. The within subjects component is a combination of 3 factors: data generating distributions, data relations, and the type of truncation. For the 2 data generating distributions, we first consider a beta distribution, which is approximately Gaussian. We also consider a truncated Pareto distribution, which serves as an example for situations where the data has an outlier. We also consider 2 types of data relations, specifically concordant data relations and discordant data relations. Concordant data relations are those where the direction of the inequality sign is the same. Discordant data relations are those where the direction of the inequality sign is in reverse. We also consider 3 kinds of truncations: no truncation, monotonic truncation, and non-monotonic truncation. Note that it is mathematically impossible to perform a non-monotonic truncation for discordant data relations, and the exact amount of truncation is uniformly sampled from the interval of monotonic truncation and non-monotonic truncation respectively. We also consider 2 types of tasks: comparison tasks and estimation tasks. To summarize, we have 2 data generating distributions, 4 data relations, 3 truncations, and for each unique combination of distribution relation cut, there are 2 repetitions. This gives us a total of 40 trials and 2 attention checks. And here's an example question that we show to the participant. We recruited participants and randomly assigned them one of 4 tasks. Participants then go through 4 training trials with feedback before seeing the main study. After the participants finished the main study, we collected demographics related information from them. Finally, here are the results. A total of 136 participants were recruited from Prolific.co. Each task had about the same number of participants, and we used a multi-level Bayesian logistic regression model for binary responses obtained from the comparison tasks. Also, we used a multi-level Bayesian hurdle-like normal model for numerical responses obtained from estimation tasks. Here are the total results for the task compare gaps. Specifically, we're looking at the posterior density of the probability of success, and the pink stripes represent the empirical mean. Overall, participants had good performance with posterior probability of success around 90%, with slightly worse performance for discordant relations. Here are the total results for the task estimate gap. Specifically, here we see that compared to no truncation or monotonic truncation, non-monotonic truncation has worse performance. Here are the total results for the task compare ratios. Specifically, for both concordant data relations and discordant data relations, we see that non-monotonic truncation has much worse performance compared to no truncation, while monotonic truncation slightly increases performance. Here are the total results for the task estimate ratio. Specifically, we see that both non-monotonic and monotonic truncations have bad performance, but non-monotonic truncations has worse performance compared to monotonic truncations. Recall that we had 2 hypotheses. First, we hypothesized that monotonic truncation would not impact DVT, Second, we hypothesized that non-monotonic truncation would adversely impact DBT. What we found is that for tasks examining a quantity whose data relation is unaffected by truncation, then truncation has little to no effect on user performance regardless of whether it's a monotonic truncation or not. And for tasks that examine the quantity whose data relation is affected by truncation, monotonic truncation has similar user performance as no truncation, but both are much better than non-monotonic truncation. Based on our results, we have the following recommendations. When the designer has control over user tasks or knows with high certainty the tasks a visualization would be used for, and when the task examines quantities that are unaffected by truncation, so for example, compare gaps and estimate gap, then the designer can truncate the axes to elicit the desired subjective perception of effect size or make the visuals more task-aligned, as recommended also by previous work. However, if the tasks examine quantities that are affected by truncation, so for example, compare ratios and estimate ratio, then we suggest performing monotonic truncations or no truncations to avoid creating visual relations that are contrary to data relations. In other scenarios, when the designer does not have control over user tasks or is uncertain about the tasks that visualization would be used for, then fixed truncation in a static visualization, such as those tested in this paper, is likely inappropriate. However, other approaches that use interactivity to gain the potential benefits of truncation without introducing deception may be effective. In terms of limitations, we did not look at the cognitive aspect of graphical perception, and we foresee several possible directions for future work, including considering structure-preserving functions for different tasks, imposing time limits on our tasks, and considering Pareto frontier of trade-offs for different tasks. Thank you for listening.